Hello, everyone, and welcome back. I hope you're all doing great. Thank you so much for your amazing support. Every like, comment, and subscription really helps this channel grow and motivates me to create more high quality Physics 2 lessons for you. Now, let's continue with another important exam style problem from the electric field chapter. In this question, we have an electric dipole made of a positive charge and a negative charge. Our goal is to find the electric field at point P, which lies on the dipole axis. Then, we'll simplify the result for points that are very far from the dipole. First, let's take a look at the figure. Before starting the calculations, notice a few important points. As we learned earlier, we determine the direction of an electric field by imagining a small positive test charge placed at point P. The electric field always points in the same direction as the force acting on that positive test charge. Therefore, the field produced by the positive charge points away from the positive charge, while the field produced by the negative charge points toward the negative charge. Also, both electric fields lie along the z-axis, so we only need to combine them algebraically according to their directions. Now, let's solve the problem step by step. Step 1. Determine the distances from point P to each charge. The distance to the positive charge is z minus d over 2, and the distance to the negative charge is z plus d over 2. Now, let's continue with the solution. Step 2. Write the expression for the net electric field. Before substituting the values, remember that z is the distance from the center of the dipole to point P, and d is the distance between the two charges. From the figure, the distance from plus q to point P is z minus d over 2, and the distance from minus q to point P is z plus d over 2. Now, substitute these distances into the electric field equation for each charge. After simplifying, we obtain the exact expression shown on the slide. Step 3. Now consider the case where z is much greater than d. This means d over 2 squared is very small compared with z squared, so we neglect it. The equation simplifies to 2kqd divided by z cubed. Finally, using the dipole moment P equals qd, we obtain the final expression, E equals 1 divided by 2 pi epsilon naught multiplied by P divided by z cubed. This important result shows that the electric field of a dipole decreases as 1 over z cubed. Now, let's move on to the next important exam style problem. Now let's continue with exam type 4. In this example, 3-point charges are placed at the vertices of an equilateral triangle. 2 charges are known, and we need to determine the magnitude and sign of the third charge so that the net electric field at the center of the triangle is 0. First, let's take a look at the figure. Before solving the problem, notice a few important points. The center of an equilateral triangle is equidistant from all 3 vertices. Let's call this common distance r. Also, remember that we determine the direction of each electric field by imagining a positive test charge placed at the center. The electric field always points in the same direction as the force acting on that test charge. Since Q1 and Q2 are positive, both electric field vectors point away from their charges. The direction of E3 depends on whether Q is positive or negative. Now, let's solve the problem step by step. Step 1. Since Q1 and Q2 have equal charges and are the same distance r from the center, their electric fields have equal magnitudes. So E1 equals E2 equals K times 1 microcoulomb divided by r squared. Now, let's continue with the remaining steps. Step 2. The angle between E1 and E2 is 120 degrees. The resultant of two equal vectors separated by 120 degrees has the same magnitude as either vector, and it points straight upward along the symmetry axis. Therefore, E12 equals E1 equals E2. Step 3. For the net electric field at the center to become zero, E3 must have the same magnitude as E12, but point in the opposite direction. Set the magnitudes equal. K times the magnitude of Q divided by r squared equals K times 1 microcoulomb divided by r squared. Cancel K and r squared, and we obtain the magnitude of Q equals 1.00 microcoulomb. Finally, to produce a downward electric field that cancels E12, the third charge must be positive. Therefore, Q equals positive 1.00 microcoulombs. That completes exam type 4.